Welcome to POWTECH Virtual Talks on Rare Earth Elements and Energy Revolution. Jürgen Gassmann from Fraunhofer, IWKS, will talk about closing the value chain for rare earth permanent magnets. Enjoy the talk.
Welcome, Jürgen Gassmann. Mr. Gassmann is from Fraunhofer. He finished his studies in the field of material science in 29 at TU Darmstadt. Afterwards, he joined Fraunhofer IWKS and started working on recycling of rare earth permanent magnets. Since 2017, he is the head of magnetic materials department at Fraunhofer. Mr. Gassmann's topic today is closing the value chain for rare earth permanent magnets. Mr. Gassmann, we look forward to your presentation on this exciting topic. Yes, please activate your...
Thank you for this kind introduction. I think you can hear and see me now. I'm sorry, I switched the topic a bit. However, the same content is shown here. So today I want to talk about rare earth elements. Of course, we will need these materials in electromobility, and I will also talk about recycling aspects in terms of circular economy. So where do I come from? I come from the Fraunhofer Society, which is the biggest society for applied research in Germany. We have about 74 individual institutes located all over Germany, with about 28,000 people working at Fraunhofer. Myself, I come from IWKS. We are located right in the center of Germany, next to Frankfurt. So we have two sites, one in Hesse and one in Bavaria. And the main focus of our studies are critical materials, like they are used in permanent magnets, but also in batteries or in other kinds of fertilizers, for instance. We are doing research in terms of substitution, in terms of recycling, and also life cycle assessment, for instance. So the motivation of my talk today, basically, we all know that there is a global warming, and within the Paris Declaration, there was a 1.5 degree goal set for the global warming. Today, we are already at 1.2 degrees C in 2020, and so this goal was for 2100. So the projection shows us either way we are acting, we will end up beyond this value, more or less somewhere between 1.6 or 3.9 degrees C global warming increase. So it's a quite drastic gap, and it's not clear what future really brings. However, what is really clear is we have to change some stuff. We have to decarbonize our mobility sector, for instance, and our energy sector. We can do that worldwide by using renewable energy sources, by the electrification of the mobility sector and the industry. And all these new types of technologies, they will need another kind of material. And there where we are doing our research for, since some of these material may face some problems since they might be considered as critical. And here we think that a circular economy for these functional materials will be key for future applications. So have a closer look, for instance, for the electric vehicles. We had last year, the year before that, 2019, and different kind of scenarios shows us, independence of how much CO2 should be substituted, that we will need in the year 2030 about 140 million to about 240 million electric vehicles worldwide. Of course, these vehicles need a motor, which is an electric motor. And here, the most efficient motors have something like 1.2 to 2.5 kilogram of permanent magnet inside. So the demand for this material will be increased in the next 10 years about 40%. And the question is how to deal with this issue, how can we meet this demand? Next to the permanent magnets, we also need other kind of materials for storing the energy. For instance, in lithium-ion batteries in a car, it's about 300 to 500 kilograms of material inside, independent of the range, how far the car can drive. So there are different kind of scenarios how one can deal with this instance. So first of all, substitution of critical materials. This is a natural rare earth basket of the elements, and most promising is the element neodymium in neodymium oxide. About 15% in the rare earth ores is about neodymium, and the mining is driven by this element. However, during mining of 1 kilogram of neodymium, also 1.5 kilogram of lanthanum and 2.5 something about kilogram of cerium is mined, and these materials can also be used in permanent magnets. So there is research going on in this field for using the natural rare earth balance of rare earth elements for producing magnets, since this materials is mined more than it is needed at the moment. So it's more or less somehow dumped after mining. The second way is to use new mines to explore new sources of rare earths. So at the moment, the most rare earths came from China, and also Australia has a small share of the rare earth mining. However, the reserves are also spread in other kind of regions worldwide. For instance, in Russia, but also in Brazil, there are severe rare earth content in ores. So also these can be used for producing new kinds of rare earth elements. So a new source for new rare earth elements. Last, we use so much material in our products also nowadays, so we can also reuse these materials, because at the end of life, it's not damaged or broke. So it can be collected at the end of life. It has to be disassembled from the product, and then with different kind of technologies, new permanent magnets, recycled permanent magnets can be produced, and this can help to meet the huge demand for permanent magnets in the future. So in terms of magnet recycling, different possibilities are available. It most likely dependent on the type of scrap material one can get, either if it's like very mixed material where it's pretty hard to separate the magnets from the non-magnetic material. In this case, it may be feasible to recycle the materials back to the pure elements. So to go back to neodymium, dysprosium, praseodymium, and these materials can be used as they could be used as materials from primary mining. So all products are available with that. Another way for neodymium iron boron is a short loop recycling. So in this case, one can stay within the alloy system of neodymium iron boron, and a recycling is more sustainable because one needs less energy, one needs less chemicals, and one can produce recycled products with very good properties. So this is one of the focuses of IWKS, to have this functional magnet-to-magnet recycling. So this is where we do it in Hanau at our institute. We have a lab factory for permanent magnet production in a batch scale of about 10 to 50 kilogram. So we do it for a demonstration of small magnet batches. We can produce sintered magnets, we can produce Hockeyford magnets, and we also can produce polymer bonded magnets. for recycling, but also for substitution purposes. So the basic process today I want to focus is on the sintering because it's a powder metallurgical process. So we heard a lot about powder milling and about particle size measurement today. Here the whole process is shown. Some of you might be familiar with it. By recycling, we start with an end-of-life magnet, which is cleaned and demagnetized in this case. Then one can go to the hydrogen decubitation process, where the material is powderized by the help of a hydrogen atmosphere. Afterwards, the material is milled to a particle size in the range of 3 to 5 micrometer. Here we use two types of mill, one a conventional fluidized bed jet mill and also a target jet mill for producing powders. After that, the powder is aligned and compacted for be pressed to a green body, and this is sintered and annealed under protective gas atmosphere. So then one ends up with magnets. After a surface treatment and cutting and grinding processes, it can be also coated, but it can also be further optimized by different kind of processes to further increase magnetic properties. So here's the process shown for hydrogen decubitation, like it was developed already in the early 19th in UK. So basically, the magnet is shown in a hydrogen atmosphere with after different times. One can see the hydrogen is diffusing into the magnet. Stress is occurring, which powderizes the material. And this powder can be directly used for producing recycled magnets. Additionally to that, one can also use this process for separating magnetic materials from non-magnetic materials. Like in this case, it's shown by a rotor where permanent magnets are located under these metal plates. After hydrogen decubitation, one can see the rotor is totally unaffected by the hydrogen process. However, the magnet is powderized and can be separated by sieving. Afterwards, the powder is produced to magnets like I showed before. So doing so, for magnets, two most important values are the coercivity shown here. So the coercivity should be as high as possible, and also the remanence, also here, remanence as high as possible. And the demagnetization curve is dependent on different properties. On the microstructure of the magnet, which is dependent on the powder size one is using for producing the magnet, on the chemical composition of the magnet, either if there is heavy rare earth containing magnet or serum containing magnet, or if it's pure neodymium iron boron magnet, can influence the magnetic properties. And of course, like shown here, with recycled powder in green and with optimized magnets in blue and red, also a blending can occur during the processing. So in this case, we added heavy rare earth hydrides for increasing coercivity. So it's pretty easy to meet specification even with recycled products from end-of-life magnets when this material is blended and is produced like magnets from elements. Further, one can also use the well-known grain boundary diffusion process, for instance. In this case, the amount of heavies needed for getting a higher coercivity is less, since the material, the heavier earths are just located at the grain boundary phase, and since it's a nucleation type magnet, it's a location where it's needed, and it's not needed in the middle of the grain. So with this technology, the magnet properties can be further tuned. So we as research institution, we are also asking ourselves, so is there maybe something like natural footprint of a recycled magnet? For this, we use also in-depth analytics like local atom probe tomography. In this case, the sample is shown here. So basically the sample is in the nanometer scale. So here we have about 600 nanometers. So it's a very local, sensitive, atomic resolution detection method. Basically, one can measure the composition on the atomic scale. So for us, the most interesting part is the region of the grain boundary phase, which is also shown here, and here in detail for different kind of elements. So first, one can see, of course, we have an enrichment of neodymium on the grain boundary phase. Also copper and gallium is enriched in the grain boundary, and dysprosium due to the grain boundary diffusion process is somehow also diffusing a bit into the core, into the 241 core. However, what is interesting is also this gallium information that it seems to be agglomerated directly at the interface between the 241 grains and the intergranular phase. So if one checks that after directly after sintering, here we see the signal of neodymium, the signal of copper. We see the grain boundary phase right here in the middle, and also the signal of the gallium elements. So when we check that, we see that we have an intergranular phase size of about 1.4 nanometer, and the gallium is somehow distributed Gaussian type after the sintering. However, to increase magnetic properties, the material is annealed at lower temperatures. And in this case, we see the same elements. However, the behavior is slightly different within the gallium signal, like I showed you before. We see this gallium double phase, which is shown here. So first, it is obvious that the intergranular phase is doubled in size, and the gallium is agglomerated directly at the interfaces, and this better decoupling of the 241 grains is causing an increase in coercivity for permanent magnets. However, this is true not only for recycled magnets, it can also be shown for magnets produced from pure elements. So switching gears a bit to application, we had a public funded project where we checked a permanent magnet properties in terms of mechanical stability for flywheel energy storage. And in this case, the flywheels can be used for storing huge amounts of energy for a very short time. For instance, for public transportation, this could be very interesting. The material inside such a flywheel is rotating with very high wheel speeds, and therefore the stresses to all the materials with this high rotation frequency is very high. Therefore, the mechanical properties of also magnets need to be improved. So we did that from scratch. So we started by strip casting, which is a state-of-the-art technology for producing permanent magnets. Here's the material. The melt is cooled on a metal cooled wheel, and flakes are produced with a proper chemical composition and a microstructure which is feasible for producing permanent magnets. So here are the flakes in a collection chamber, and basically this is a microstructure one needs. So one has lamella distances of about 3 to 6 micrometer in distance, and these are rare earth-rich phases which are needed to produce permanent magnets. So after the strip casting, a milling procedure is following. We measured, we milled the material to particle sizes to 2 to 5 micrometers. As smaller we milled, as higher also the amount of fines were in our product in this case. So it is well known that with changing the grain size, also magnetic properties are changing. Smaller materials show a higher coercivity. However, it's also harder to align them, therefore remanence is decreasing. For us, what was important, and this was analytics was done by our colleagues from Aachen in this project, were the mechanical properties. So we measured with a four-point bending setups the failure stress of the material. First, we did it for commercial references which the customer used for his application. It was the very same grade from the same supplier, but different kind of batches. And here in green, one can see that the 25 samples for each batch we measured show different kind of properties in terms of failure strength. With the material we produced in the project, we could reproduce this material which was used commercially, and with decreasing the particle size, also the failure stress could be increased about 50 megapascal. So the take-home message is, of course, with the powder metallurgical process, the mechanical properties of sintered magnets can be tuned. One has always like a balance between mechanical properties and magnetic properties, but we think that the secondary properties like the mechanics is also very important for applications. We saw that when material is failing, it was an intergranular failing, and with further modification of the grain barrier phase, also the properties could be further improved. So with this, I'd like to sum up my talk. I hope I could show you that rare earth elements will play a key role in the decarbonization of our society, since all this new technology we are applying right now need also new materials. The rare earth demand will increase very much because of the change in electromobility in the next 10 years. And to increase sustainability of all these products, circular economy will be needed in Europe and also worldwide. So thank you for your attention, and I'm looking forward